All right, team, we're going to talk about calculating statistical power with an example here. And just as a quick review, when we're talking about power, we are talking about the probability that our sample and our experiment essentially will correctly reject the null hypothesis, if in fact we come from an alternative distribution. So what we're looking at here is the distribution in black that represents the null hypothesis. So if we're considering, in this case, a one-way, we'll just say significance test, right? We're going to be comparing our samples. We're going to get an X bar. Let's just say X bar comes over here, and I'm going to make that green. So X bar is going to be somewhere over here. And X bar could be from the null distribution. It just could be a really unlikely value to have occurred, or it could come from this alternative distribution. And what we're trying to calculate is the power or probability that our test will, if X bar comes from the alternative distribution, the probability that we will reject the null hypothesis. And so let's just say that our Z score, we did Z1 minus alpha right there, and alpha represent, or 1 minus alpha represents that area. For alpha is equal to 0.05, we're looking at a 95% significance test, and that's that area over here. This is the 0.05 area. So that represents our type 1 error. If X crosses that threshold, the Z value for X crosses that threshold, then we are, and in fact, that sample came from this null distribution, then we still have this little bit of chance, this 5% chance that we're going to incorrectly reject the null hypothesis, a type 1 error. Okay. Now power gets to the kind of flip side of that. In class, I talked about this as like dark matter, like we're inferring the distribution for the alternative hypothesis. We don't know what that population looks like. We don't know what the true population mean is. We just have this sample and we have the standard deviation and n, right? And so if X bar did in fact come from mu alpha or the distribution, the alternative distribution, we want to know the probability that we would correctly say, hey, you're part of this family over here, not that family. And we want to know the probability that we will correctly reject the null hypothesis. Okay, so for over here, this is what we call beta, and that's our type 2 error. So beta is equal to type 2, that's a false negative, incorrectly not rejecting the null hypothesis. You take that pregnancy test, it says you're not pregnant, but you can feel the baby kicking inside, right? Like that's a false negative. And then 1 minus beta is equal to power. So this is over here, this is our probability that we will correctly reject the null hypothesis, right? So depending on how far mu alpha is from mu naught, depending on the standard deviation and the sample size, those all influence power. So we're trying to calculate this area over here with some inferred distribution representing the alternative hypothesis. So let's go down to our example. We've got the city of Grand Junction, and it is, this is a real thing. It does have a wastewater treatment plant that generates methane that is kind of scrubbed and piped and used to fuel buses and garbage trucks and all these good things. So it's a real thing. Now this is all made up after this. So say they want to upgrade their treatment plant to increase the methane yield. Let's just say the current concentration that's coming out of there, I don't know if yield's the right word, but is 80 parts per thousand. And then we've got this new treatment process that the city is considering and investing in, right? It's going to cost millions of dollars to upgrade the treatment process. And if they can get one more part per thousand, if they can go up to 81, then it'll be worth their investment. So we're going to explore how we can use the normal distribution here, which is an assumption we're making, to then calculate the power of the test. All right, so I'll note that the standard deviation based on past measurements of that concentration or yield is 5 parts per thousand. All right, and then we're looking at doing a bench test, right? So we're going to do this kind of lab scale test to figure out if the new treatment process will increase the yield. And we're going to do 50 samples. So N is equal to 50. All right. So first we're going to look at our what our null hypothesis is and what our alternative hypothesis is. So H naught, we've got mu naught is equal to 80 parts per thousand. And if you're doing a significance test, you would write it something like this: mu alpha is less than or equal to 80 parts per thousand. Okay, but for our power test, we're going to kind of ignore that part. All right, and now our alternative hypothesis is that mu is in fact the population that is represented by the alternative hypothesis is greater than 80 parts per thousand. And in fact, we're going to set it to 81 for this particular test. All right. So that's going to be, this is going to represent our alternative distribution. And so that's going to follow, we're going to assume that is normally distributed, right? So this is assuming that the null hypothesis, or that the null distribution is also normal, which works if we're dealing with means. So means of a certain sample size. In this case, we're 50. So if a sample size from a mean of approximately 30 or greater, that will follow normal distribution. So we're in good shape there. All right, so now what we need to do is set up some stuff that we're going to test. And I think what I'll do is just draw this out, and then we'll kind of fill in the gaps from there. So let's go ahead and get our null distribution and alternative distributions. All right, so there is 80. So that represents mu naught. Okay, so I'm writing this in a real scale here. So this is a scale of parts per thousand. So X instead of Z scores, right? And then what I want to do is, let's just say here's our alternative distribution that we're going to see what is the power of this if we're assuming that it's 81 parts per thousand for mu alpha. All right. Now, clearly these are going to overlap. We don't know how much they overlap based on the standard deviation. But what we're going to do now is calculate first the critical Z-score. So this is going to be, let's just write it here. So we're going to do B, calculate Z1 minus alpha. And we're going to calculate that Z-score both for this null distribution and for this alternative distribution. And I'll show you how we do that. And really, we're going to end up translating this Z-score to the real world units here of parts per thousand. All right, so we're going to set alpha is equal to 0.05. So we need Z of 0.95 for a one-way test. And then if we look that up in our tables or cumulative distribution function in Python, we end up with 1.645. So that's going to be our Z-score. And then, because again, we're dealing with parts per thousand, we want to translate that Z-score to a real world value. All right, so to do that, it's not quite magic here. We're going to say calculate the part per thousand value for Z.95 is equal to 1.645. And so all that is using that Z-score function. So Z is equal to X bar minus mu over S square root of N if we're talking about the distribution of sample means. So we've got our Z-score and we can solve. So that is going to give us the following. So we're going to get mu naught plus z 0.95 times s over square root of n. This is kind of like a one side of a cumulative distribution function. And that's going to give us our critical z value. So this is 80 plus 1.645 times 5 over square root of 50. Okay, and so that ends up equaling 81.16. So I'm going to write that over here. So that's 81.16. So just over 81. And what this really is so 81.16, that represents z.95 just in parts per thousand units. All right, so all we did was we took the mean, we added the z-score and multiplied it by the standard deviation. And that should give us on this side, that should be 0.05 area under the null distribution curve, right? All right, so that's great. But we're not done. We haven't calculated power yet. That's just our z-score. So now we need to actually calculate the area under the curve. So it's going to be part C here. And I'm just going to go ahead and erase this for room. Okay, so now we're going to calculate area under HA. All right, so this is H naught. This is HA distribution to the right of 81.16, which is our Z 0.95. All right, so that right here will be our 1 minus beta. This is beta, this is 1 minus beta. So to do that now, we're going to figure out the z-score associated with this null distribution. So find z-score of 81.16 based on the null distribution. All right, so HA follows normal, mu alpha s over square root of n. So what we, just to kind of look at how we got to where we are, we set the z-score based on alpha of 0.05, calculated that z-score. We translated or converted that z-score into an actual units based on the null distribution value, okay? So I was like, step one, we got over here, 81.16. Now we're going to convert that back into a z-score and calculate the probability. The z-score allows us to calculate the probability or the area under the curve of the alternative distribution. So we're kind of like, it's like a hop and a skip. We hop over here based on the null distribution, and now we're hopping into the alternative distribution and calculating that probability. Okay, so Z, we're going to call that Z of, we'll call it Z alternatives. This is based on the alternative distribution. So we get 81.16 minus our mu alpha, or mu alternative, sorry, divided by S over square root of n. And then that's going to be 81.16 minus 81 all over 5 square root of 50. So that's going to get us a kind of a small value. It's going to be 0, should be negative, right? So negative 0.23. Okay, so I didn't draw that correctly, right? It's actually going to be on this side of that distribution. So it's a negative z-score. And then if we put that into our value to calculate this, so we're going to look at this. So calculate the probability or area to the right of negative 0.23. Oh, you know, I got that wrong. So that's not negative. So it's positive. Okay, great. So we are just a little bit on this side, right? So we're really close to the mean. We're just on that side of the mean, right? So to do that, then we can do the following. So this is just when you look at our fee tables, like this is just the CDF of the normal distribution. We plug that 0.23 z-score in there, and that's going to give you the area up to that value, right? So the cumulative distribution function gives you the area from the left up to that value, cumulative probability. So we're going to want to calculate the following, which is just a complement of that. So area to the right is going to equal of ZA is going to equal 1 minus that. So we're just taking the complement. So we plug that value in, and we can look that up in our tables. We could do 1 minus norm CDF using the Python functions, the 0.23 standard normal distribution, and then that gives us 0.41. Okay, so what that means is we have a 41% chance of correctly rejecting the null hypothesis. So I'm going to go ahead and say that's low power. All right. All right, so there's a couple other things we can consider then. And what I want you all to do on your own is the following. All right, so I want you to calculate the power of the same test or this experiment, we'll call it, assuming that N and S are the same, but that the effect size increases. Okay, so now we're going to look at an HA of mu A is equal to 82 parts per thousand. All right, so now we're going to shift that distribution a little bit farther apart and say, okay, if we are trying to determine a difference of 82 parts per thousand, what is the new power? And might not be super intuitive because we're not actually talking about a sample yet or a sample mean. But now what we're thinking about is if based on this sample, we've got this standard deviation, we've got this n, we don't have an x bar yet, right? We don't have the actual x bar. But now that we're trying to determine something that's a little bit farther apart, let's see if I can drag this. Okay, we're scooting that over here a little bit more. Let's just say over to here. And then I'm going to change that to 82. Now you can see that we probably increase the area on this side, right? So we probably increase the power. Again, we don't have a sample, we don't have an X bar, so we don't know if we're going to reject the null hypothesis or not. But based on this new effect that we're looking for, now all of a sudden that alternative distribution is a little bit farther apart from the null, and by doing that, we're increasing the power, we're increasing this area on the right side of our Z1 minus alpha. All right, so I want you to do that. And then the last thing I'm going to walk you through is just one other example here. So let's say we want a certain power. And let's just say that power, we want it to be 90.9 or 90%. All right. What sample size do we need to achieve that power? All right, so we're going to go back to mu naught is equal to 80 and mu alpha is equal to 81. All right, so we're going to go back to that original example. All right, so to do this, we are going to, let me just draw it first. Okay, there's mu naught, and we're going to write it as 80. And then we've got mu alternative, and that's 81. We are going to say that we're going to have our z 1 minus alpha. And what, in order to achieve that power, we basically need the, if this power over here is going to be 0.9, we need this power, we need that type 1 or type 2 error beta to be 0.1. All right. And so what we can do then is make sure that the z-scores associated with this distribution and this distribution line up in such a way that that's in fact the case. Okay, so I'll write this out as follows. We're going to have mu naught plus z1 minus alpha s square root of n. That gets us to here, right? From that point, from that location. So that's going to be the z alpha, and it's going to be in terms of parts per thousand. And we want to set that to equal 81, and then we're going to do minus. So minus, because we're going this way, right? So minus z, and we want that beta right there to get us so that this is 0.1 times s squared root of n. All right. So all we said that is that we want these two values, which are going to be values of parts per thousand or units of parts per thousand. We want those two values to be the same. So this side, it gets us our ability to have our significance sets at the 95% level. And then on this side, it says, okay, we're going to adjust our distribution based on n, we're solving for n, such that this will be achieved. And this z beta sets this value over here. So z beta, based on the alternative distribution, it sets that value to 0.1. So we already looked this one up. This is 1.645. This is z beta. Let's figure out how to calculate that. So this is going to be z, and that's going to be 0.1. So that's the cumulative probability up to that point. So this is where you do the following. You say, I'm going to go look up norm.cdf, and I'm going to put, oh, no, I guess that's not going to work. It's norm ppf. Norm ppf, we put in 0.1 and it spits out a z value. It's basically just an inversion of your table. So if you go to your z tables and you look at the cumulative probability on the kind of rows or columns, and then you find the z-score associated with the cumulative probability of 0.1. So that ends up being z is equal to negative 1.28. All right. So we'll plug all these numbers in. So we get 81 plus 1.645 times 5 over square root of n is equal to 81 minus negative 1.28 times 5 over square root of n. Solve for n. And then n ends up being about 214. So that's how many samples we would need to discriminate this effect if in fact there's only 1 parts per thousand off or, above, small effect, right? With a power of 90%. So 90% of the time we get a sample x bar s square root of n, and we are going to correctly reject the null hypothesis. All right, that's all for now.